right. So in this lesson we're going to start looking at what are called electric fields and look at how does an electric field help me describe what is going to happen to a charged particle. So the way we talked about calculating what happens to a charged particle kind of in the last couple of lessons was to use what's called Coulomb's law. And what Coulomb's law really is, it's a way of figuring out the force acting between charged particles or acting on one charged particle due to other charged particles. Coulomb's law works pretty good if you have discrete individual charges. Where Coulomb's law starts to become difficult to use is when you have, say, a distribution of charges. Say like a sphere where the charge is uniformly distributed over the sphere, because R changes. That distance between the charge you're putting close to it and the charge of the sphere itself is different. One way that we can begin to describe this is to calculate what's called an electric field, which basically is a way of describing mathematically how our charged particle is going to interact in this region of space. Now, electric field is not really, well, I don't know if I want to say it's not a physical thing, but because it obviously has an effect on objects around it, but it is a way of describing this force at a distance a little bit differently mathematically in a way that actually is a little bit more useful to us. So, what electric field really is it's the measure of force acting on a charge per unit of charge. So if we wanted to figure out the electric field at a location, we could put a charged particle at that location, measure the force acting on that charged particle, and divide it by how big the charge is, and you find the electric field. So for a point charge, or a test charge is another way to describe this, the electric field is going to be equal to force divided by the charge that you're measuring the force on, or K times Q, where Q is the other charge in this system, divided by R squared. So the units for electric field, the most common units you find are newtons per coulomb, force per charge. So electric field happens to be a vector, and so we have to have a way to describe this vector in terms of what its direction goes. The way we generally describe this vector is that the electric field points away from positive charges and toward negative charges. So the way to think of electric field is, when we're talking about the force that's acting on it, it's really the force that a positive charge would feel, is the direction the electric field goes. A negative charge would obviously feel the opposite force, or a direction opposite the electric field. So if you release a positively charged particle, what would happen is it's going to travel in the direction of the electric field. If you released a negatively charged particle, it's going to travel or experience a force in opposite the direction. So here we have how electric field looks for both a positive and negative point charge. We can look at some combination of charges. On the left we have what I would call a dipole, a positive and negative charge close to one another, and that's what the electric field looks like for a dipole. Goes away from the positive charge, goes toward the negative charge. So it looks something like that. Now, the cool thing with this is if you take a magnet and put iron filings close to a magnet, you get a similar type of pattern, because the magnetic field caused by a magnet and the electric field caused by a dipole look really similar to one another in terms of their shape. Now, if you have two positive charges, we might end up with a location in here where the electric field is 0, where they're being canceled out. So let's look at a couple of problems. The problem that I have first is we're going to have 3 point charges. Each one has a magnitude Q, and they're all on the y-axis. And one is at the origin, one is at y is equal to a, and one is equal to y equal to negative a. And the arrangement I have here is shown on the right. And what we want to do is find the electric field at some point P that is a distance x away from the origin. So point P is on the x-axis, and it's a distance x away from the origin. And so we want to find the electric field at this point, or the total electric field. Now, the way to do this is to find the electric fields from all 3 point charges, and then do vector addition to add all 3 of those vectors together. So if we look at what the electric field looks like from the point charge that's at the origin, it just looks like this. I'm going to call this E0, kq over x squared. For the point charge that is at point A, well, it's an angle theta away from it. And for negative A, it's also the same angle theta. The only difference is there's Well, one points down in the left and one points up or down to the right and one points up into the right. Now, one thing to point out about R1 and R2 is that we could use Pythagorean's theorem to figure out R1 or R2, that it should be x squared plus a squared equals r squared, or r equals the square root of x squared plus a squared. Another thing that might be important to figure out is sine and cosine. And the reason why it might be important to know sine and cosine in terms of a and x is that one of the in order to add vectors together, I probably need to break the blue and green vectors up into x and y components. So let's look at what's happening here. Now, it's worth pointing out that for the blue and green vectors, their y components cancel each other out. X and a are the same. So sine is the same. One's just going to be negative a over x squared plus y, a squared square root. And the other one's going to be equal to a over the square root of x squared plus a squared. And those are going to cancel each other out. However, the y components will not cancel each other out. So what I've done here is I've taken k, q over r squared, or in this case, my r squared is x squared plus a squared, times the cosine of theta. And the cosine of theta, if we look back, was x over the square root of x squared plus a squared. So if you take and multiply all this together, the x component for both vector are both the electric field from the one that is a above the origin and a below the origin. Looks like k, q times x over x squared plus a squared to the 3/2 power. Now we'll check the y components and make sure they cancel out. The y component of the one at the origin is 0. The other two are k, q, a, x squared plus a squared to the 3/2, and then negative k, q, a, x squared plus a squared to the 3/2. Now it's worth pointing out that those two do add up to 0, which we already thought was going to be true anyway. So we want to find the net electric field at point P. I'm going to add all those together, and if you add those together and do a little bit of simplification, you get that equation there, that the electric field at point P is in the x direction, and that it's k times the quantity q over x squared plus 2qx over x squared plus a squared to the 3/2 power. Now it's worth pointing out if we do a few things here, like if we make x really, really, really big, let's say. So let's say we made x very large in comparison to a. So if we make x very large in comparison to a, the bottom part of that x squared plus a squared basically becomes x squared. And so you get qx over x squared to the 3/2. X squared to the 3/2 becomes x cubed. And so you get q over x squared. And so if you make x really, really big compared to a, this thing is going to look like 3 charges all at the origin. Now if we kind of did the opposite and made a really big compared to x, so put it really, really close to that particle, what you start to see is that this value soon approaches, we can actually work it out, it doesn't necessarily approach 0, but it starts to get smaller and smaller, in which case we almost get something that looks like, or this gets much bigger compared to this. So that's kind of a quick overview of how to do some electric field calculations dealing with point charges. In the next lesson, we're going to look at what would happen if I have not just 2 or 3 or 4 point charges, but what about a distribution of charge? How do we begin to deal with problems with distributions of charges and calculating their electric fields for those types of situations?